Thanks. So good afternoon, everybody. Mechanisms leveraging arbitrary belief hierarchies. I'm Jing Chen. I just got my PhD from MIT, and now I'm doing a postdoc here. So this is joint work with Sylvia Micheli and Raphael Paz. So my PhD focused on mechanism design, which is closely related to many disciplines, like economics, like mathematics, like computer science, etc., etc. In particular, from theoretical computer science, why do we want to connect mechanism design with theoretical computer science and mathematics? Now, on the one hand, what mechanism design does is it tries to obtain private information from selfish players using their rationality by giving them proper incentives. Well, on the other hand, in theoretical computer science and mathematics, we do a lot of optimization. But we typically assume that we have the correct data as input. We have the information. Now, if you put these two parts together, what do you get? We can do optimization without information. And in fact, we can allow the decision maker to be totally ignorant. He has no idea about the private information of the players, and yet we enable him to optimize based on those private information so that he can choose his own desired outcomes. Isn't this amazing? Now, actually here I have a very good example about that, about this a very simple mechanism design problem. So this is a single good auction. So we say there's a seller, he tries to sell a vase. And then we have a bunch of players, 1 through n. And each player has a private number in his mind, his value about the good, how much he's willing to pay. The seller is trying to get as much money as possible. So here our question is, how much revenue can we get from this auction? Now, well, of course, if the seller knew that blue player values 100 and nobody values more than that, he just give the vase to blue and charge him $99. And by doing this, the seller gets a pretty good revenue. However, of course, here the question is, the seller doesn't know who values how much. Right? Now, another question is, does the seller know the distribution from which the players' valuations are drawn? To be sure, in many mechanism design problems, we do make such assumptions. But today, in this talk, I'd like to talk about really totally ignorant decision makers so that we do not impose any probability distribution. Maybe he doesn't know this distribution, or maybe there is no distribution at all. So this is really an ignorant decision maker. Now, in this case, what can he do? And here is a classical second price mechanism, which asks each player to announce a number, which is what we call a bid. And according to this mechanism, it is well known that the best strategy for a player is to truthfully reveal his valuation, the number in his mind. So we'll see all the players report their true value, and then the mechanism gives the good to the highest bidder, which is the blue player here, and charges him the second highest bid, which is the second highest true valuation. So here the revenue in this example is $80. Not too bad compared with 100. So in general, the second price mechanism always delivers revenue equal to the second highest true valuation among the players. And of course, the question we always ask is, can we do better? And our result is, yes, we can. And actually, in our solution, in the worst case, revenue will always, in the worst case, revenue will be the second highest true valuation. But in many cases, the revenue will be much, much higher than that, and sometimes even higher than the highest true valuation among all the players. This sounds a very demanding goal, right? Sometimes we are required to generate revenue higher than anybody's valuation. Now, how can we achieve that? Instead of giving you any technical detail, I'd like to give you some strategic scenario that carries some intuition about where this more revenue could come from. So this is a scenario, the stock market. We see this every day. People buy and sell various stocks at different prices. And we all know that even a rational player may lose his shirt in such a market. Is this guy really rational? The answer is yes. But he may still act based on wrong beliefs that he may have. And a little bit more formally, those are the beliefs. So order zero beliefs is what we call, order zero belief is just his own valuation. And for sure, he may act based on that. But he may also act based on his beliefs about others' valuations about the stocks. So this is his order 1 beliefs. And also he may act based on higher order beliefs, which is beliefs about others' beliefs, about others' beliefs, etc., etc. So there is a whole belief hierarchy that the players may use. And such hierarchy may be right, may be wrong, may be totally arbitrary. And that's why this guy may still get negative utility, even though he is rational. So the stock market here just reflects a fact that higher order beliefs affect all of us. And our question is, can we leverage this type of beliefs in single good auctions? Although the scenario is very different from a stock market, but the intuition is the same. So here our answer, of course, is yes. But as we will see, higher order beliefs do not come for free. We can only leverage them under proper higher order rationality of the players. Again, a little bit more formally. So what is higher order rationality? So order 1 rationality is just the fundamental notion of rationality that we always talk about in game theory. And actually, there are many different definitions, different assumptions about rationality. And here, what we are using is Allman's notion that he proposed in 1995. And the reason is that actually Allman's notion imposes perhaps minimum requirement about the player's rationality. So if you ever want to talk about rational behavior, you'd better assume that your players behave in a way consistent with Allman's notion. So this is the weakest assumption that we need. And once this fundamental notion is there, we can talk about order 2 rationality, means I'm rational, and I believe you are rational too. And also higher order rationality. I'm rational, I believe you are rational, etc., etc. So our solution will be based on this higher order rationality. Now, this is more precisely what are our contributions. First of all, I have to define our goal, the revenue benchmarks that we want to achieve. And actually, we define a sequence of benchmarks. The order K benchmark Bk is defined over the order K beliefs. And again, the beliefs may be right, may be wrong, may be arbitrary, and the benchmark is always well defined. And as we'll see soon, the benchmark is indeed very demanding. But although it is so demanding, our theorem says that we have a mechanism that generates this much revenue from the player's order K+1 rationality. So you notice there is a gap between the order of beliefs we can leverage and the order of rationality we need to rely on. And it is actually natural to ask whether this gap is necessary. Can we reduce less rationality of the players and achieve the same result? And actually, our second theorem says that that's not possible. So order K+1 rationality is actually not only sufficient, but actually necessary. There's no mechanism can generate this much revenue if the players are just order K rational instead of K+1. And these two theorems together actually provides the first separation about the power of different rationality orders in mechanism design. Yeah, you have a question. Oh, yeah, the answer is yes, and you will see later. I will give you a little bit detail there. Yeah. So this is, from game theory, we know that different rationality orders are by definition different notions. But here, this is the first time we really see there is some goal that can be achieved under, say, order 5 rationality, but cannot be achieved under order 4 rationality. So actually, this is one reason why I choose to talk about this result here, because this actually was motivated by the audience here. So last year, I gave a talk exactly in this room, and the audience made the comment that at that time in the literature, we still don't know whether there is such a separation from the different orders. And so here it is. Yeah. And now in the maybe next 5 minutes, let me give you a little bit detail, which is how we model the players' beliefs and how we define the benchmarks. Now, once you get the model, you can think about by yourself how much information you can elicit from this type of beliefs. Right? Okay, so the higher order beliefs. This is actually very well defined in the literature by Kripke in model logic and by Allman in game theory, etc. And these beliefs are modeled as a directed graph. So a node is labeled by n numbers. N is the number of players, and it's V1 through Vn, one for each player. and each edge is labeled by a player I. The interpretation is also very simple. So here is a partial graph. I didn't draw the complete graph, but this part is enough to give you the idea. So a node, so here we have 3 players, blue, red, and green. A node represents a possible world. And you see in each world, the player has his own value, and a player may have different values in different worlds. Right? And the edges represent a player's beliefs about which world is possible. For example, here, player 1 believes that only 2 worlds are possible, and the player's values are like this and like that. Now, you notice one thing. The player always knows his own valuation, and that's why his value is always the same as his true value in all the worlds he believed possible. Now, another thing is that a player's belief may be totally wrong, like what you see here. And another thing is, here we are talking about which world is possible, instead of what is the likelihood for a world to occur. So we are not imposing any probability distributions in this model. Now, if you want to talk about higher order beliefs, you follow the graph, expand it further, and within k steps, you reach a subgraph, and this is order k beliefs. So again, it's a very clean, very succinct model. Now, given these higher order beliefs, the revenue benchmark is a function mapping each world to the revenue wanted in this world. And I want to define it just by example. So here, again, we have this world, omega. We have 3 players, and those are their valuations. And we define the guaranteed order 0 belief to be a player's own value. And the interpretation is the following. So this player believes that no matter which world he is in, there is always some player, namely he himself, who values the good for at least this much. And for all the players, we have his order 0 belief, and the order 0 benchmark is just defined to be the second highest among all of them. So it is exactly the second highest true valuation. Now, what about the order 1? Now we expand one step further to look at the order 1 beliefs. And let's say player 1 beliefs are like that. And we again define the order 1 guaranteed belief. Here, I just claim that the number is 7. And why? The interpretation is that this player believes that no matter which world is the truth, there is always some player, namely player 2 there and player 3 here, who value the good for at least 7. Now, why this number is not 9? Because 9 is not guaranteed in the upper world. Right? Nobody there values 9. So 7 is the maximum guaranteed number for him. And we can define the same thing for each player by expanding the graph to look at his belief. And we define B1 to be the second highest among those beliefs. And for the B case, you just define it from the graph following the number k, the k-step subgraph, and in a recursive way. And actually, from this definition, because we keep on expanding the graph, and actually it is pretty easy to figure out that the benchmarks is always not decreasing. So bk is greater than or equal to bk minus 1. It is intuitive that the more information we collect, the better the benchmark should be. And actually, even better is that the gap between the bk and bk minus 1 can be arbitrarily large. So even b1 can be arbitrarily large. And as you can see from this graph, so if all the players' beliefs are correct, then all the benchmarks are bounded between the second highest and the highest true valuation. But if the beliefs can be wrong, then those benchmarks can really go unbounded, even much higher than the highest valuation. This is also intuitive. It is totally possible that those 2 players, they value the good for 0, but each believes that the other value is like 100. This is totally possible. So this can go really unbounded. Now, this is really the only technical detail that I want to show you. And as you can see, it is really a very demanding benchmark. Now, the thing, how to achieve this benchmark, I'm going to hide from you. So I'm going to mark. So this is our arbitrary belief mechanism. I don't know if you can see there is something there. I don't want you to see it. You don't see it, that's correct. And, but the only thing I want to tell you about this mechanism is the following interesting property. This is what we call strictly individually rational. The question is the following. you know, sometimes we get the revenue higher than anybody's true valuation. That means, by definition, somebody gets negative utility. Now, why would the player want to get to such a mechanism? The answer is the following. So for each player, according to his own belief, his utility will always be positive in our mechanism. So he will have incentive because he believes that he's going to make money. And if this reminds you anything, I guess it reminds you about the stock market we saw at the beginning. That, you know, not everybody makes money in the stock market, but everybody believes that he is going to make money when he enters the market. So people always have incentive to go to the market. And this is the same thing happening here. So this is a very quick summarization about what we did in this work. And the last thing I want to say is that following this line, actually there are a lot of things to be done. For example, we can think about how to leverage the player's higher order beliefs in other strategic settings, like multi-good auctions, like social network, voting, etc., etc. And also, can we do better if we assume that there is a distribution where the values are drawn, and the decision maker actually knows the distribution? How much does this help, etc., etc. So, last thing, if you feel mechanism design, game theory interested, and in general, if you are interested in dealing with optimization but with respect to incentives, I'll be very happy to talk. Thank you.